Knoxville, USA in 1993. From March 1989 to December 1989, he worked in the Research and Development Electronics Division of Crompton Greaves Limited, Mumbai, India. He joined the Department of Electrical Engineering, Indian Institute of Technology, Kharagpur, India, as a lecturer in April 1994, became assistant professor in January 1996, associate professor in the year 2000 and professor in 2011. Professor Kastha has been teaching and doing research in the area of power electronics and drives for more than 3 decades now and has authored 35 journal and 60 conference papers. His research interests are in the areas of wind power generation, machine drives, DC power supply for microprocessors, and DC distribution systems. He has co-authored a book titled Wind Electrical Systems by Oxford University Press and prepared web-based and video courses on power electronics and electrical machines respectively as parts of NPTEL program of Government of India. He has also participated in several sponsored and consultancy projects in the areas of industrial robots, chaotic behavior of power electronics converters, semi-automatic electric vehicles, drives diagnostics, VSCF wind power generation schemes, and reconfigurable distribution systems. Professor Kastha has been a member of IEEE since 1994 and a senior member at present. Now I would like to request Professor Kastha to proceed further. Over to you, sir.
Thank you for the nice introduction. I will share my screen. Please let me know if it is visible. No, I'm sorry. So is my screen visible? Hello?
Yes, sir.
Okay. So I guess I will proceed now then. Where is the... Welcome. A very good afternoon to one and all. Myself, the Prof. Kastha. So introduction has already been given, so I will not spend time on this slide. So the title of today's talk is Distributed Generation and Microgrids. Now, you all know that energy is important for development and sustenance also. And there are basically two forms of energy. One is the non-renewable, which we are familiar with, includes fossil fuels, oil, coal, natural gas, etc. And the other type is called the renewable energy systems, solar, wind, hydropower, etc. Now, we have been so far been using.
So sorry to interrupt, but can you please make it in presentation mode, full screen mode?
I'm making it in full screen mode only.
Okay, but sir, it's oh,
Sir, good afternoon, sir. Sir, if possible, can you share the screen, computer screen, so it will come automatically, sir?
Okay. Well, just 1 moment.
Sure, sir.
Stop sharing.
there is some option.
Entire screen.
Yes, sir. Yes, sir. Yes, that's.
Is it
Now,
visible?
yes. Now make it full screen.
Is it visible now?
Yes, sir. It is very.
Yes, sir. Yes, sir.
Okay, so you are talking about non-renewable and renewable energy. So we have been using non-renewable energy for quite some time and depleting it very fast. Not only that, so this is the situation with non-renewable energy, that is the traditional form of energy. As per an estimate, it is going to end by 2300, but that is pretty far away still. But the more immediate problem is this, that the use of non-renewable form of energy the way we have been doing creates a lot of pollution and greenhouse gases, which finally increases the global temperature and which brings out all sorts of problems like ice cap melting and etc. These are all familiar things. So there has been a conscious effort to move towards renewable energies, and almost all government have set certain goals of doing away with the fossil fuel burning and going to completely renewable sources by some date. India also has one. So mostly of the renewable energies, the hydropower has been traditionally known. Biomass has also been traditionally known. Solar and wind are the main two sources that are developing very fast across the globe as well as in India. Now, when it comes to these two types of renewable energy, even the hydro energy, the tendency has been to go for larger and larger single units. For example, this is a solar park with 850 megawatt, and right side you are seeing one of the large wind turbines rated at 7.5 megawatt. This is some time back. Now I heard that even 15 megawatt single wind turbines are available. And not only that, they are being clubbed into wind parks where the power rating is matching that of a super thermal power plant. The reason being, of course, the economy of scale. If you make things larger, the per unit generation cost comes down. But the point is, as the technology is mature, the economy of scale gives diminishing return. So even the smaller size ones becomes almost equally economic. So we are going to that phase now. Additionally, there are several problems with this kind of renewable energy. One, the major being that they are intermittent. So sometimes you have large amount of power available, for some time nothing is available. So you see that this kind of energy production peaks that comes, peaks and troughs. So in order to, this is not good for the power system. So if you want to smooth it, you basically need storage. Now to date, there are only two technologies which can give you utility scale storage, that is gigawatt hour of storage. One is the compressed air energy storage, another is the pumped hydro storage. Now these two, although has been used, but they are very location specific. Until and unless you have certain geographical formation, you cannot use them. So it's not universal. You cannot use this storage system where you generate. The other energy storage systems like battery, flywheel, supercapacitor, etc., they have not been developed to that kind of power level yet. So here are some problems with large scale renewable generation. First of all, it needs large amount of land, particularly for land-based project. Of course, if you are using offshore wind, that is a different issue, but it has its own set of problems. Also needs large initial investment and wide fluctuation in energy production, just what I was telling. And high penetration may cause instability of the power system. Since the energy generation is erratic, it is difficult to plan assets for power evacuation. Do you plan it for the peak power or do you plan it for the average power? What? And if you design for peak power, when the wind is or resource is less, you are underutilizing your resources without storage. And as I said, large scale storage technology is still not available. Last but not the least, effect on the atmosphere is not fully understood. For example, if I say I cover millions of square kilometers of earth with solar panels, or put millions of wind turbines in the ocean, which will be churning the lower level of atmosphere, what kind of effect is it going to have to the atmosphere in the long run? These issues are not very well understood. So for some time, the trend has been going towards producing them in smaller size and many of them distributed. So this is micro hydroelectricity generation. You also have small wind turbines, and you also have rooftop solar. These technologies are coming up and becoming almost as efficient and as economical as the larger ones. So this shows the price trend. Less than 10 kilowatt rated PV system. So this has been happening for some time. But the thrust toward distributed generation came actually from an economic point of view. With deregulation, trade in energy paves the way for independent generation and thus also to distributed generation. That is, with previously electricity generation was centralized, mostly controlled by the government. Now this has been deregulated, so many people can produce. So they are producing at many places and in different sizes, not always fit for the transmission line. So that is how the distributed generation concept has come up. So what this concept is, if you compare it with the traditional form of generation distribution, the traditional form is that you have generators, then you have transmission line, then you have distribution network and consumers. Generators are only at one place. Now, compared to that, if you look at the distributed generation, you have generators, transmission line, and then you have distribution network, where also you have distributed generators, and then consumers. In fact, even consumers are now changing. Consumers can put up rooftop solar, and the new term being called is the prosumer. Okay, so this is a kind of a definition. Of course, there is no one single definition of a distributed generation system. So Sigri has given a definition, that is DG to be a generation that is not centrally planned, not centrally dispatched, usually connected to the distribution network, and usually smaller than 10 to 100 megawatt. In fact, it can be much smaller. So the main reasons for interest in DGs are as follows. You can have combined heat and power plant, particularly for captive generation. Standby emergency generation for emergency situations like in hospitals. Using DG as a cost-effective source of peak power. If you have peak power, you have some limit on peak power. If you draw more than that from the utility, you will have to pay penalty. That can be mitigated using DG. Reduction is grid losses, because generation is happening almost at the place where it is being utilized. So transmission distribution losses are reduced. They can provide also voltage support and power factor correction. Grid investment is deferred, because if the transmission load or the distribution load reduces because of renewable generation, then you need not invest in the grid infrastructure, that is putting new transmission lines or transformers. Green power, renewable are well placed as DG plants, that most of the DGs incorporate the renewable sources in one form or the other, and as well as storage.
For irrigation issues.
Yes. Is it visible and audible? Hello,
Yes, sir, you are audible, sir.
screen is visible.
Yes, sir, you are visible. And your slide also visible.
Okay, let me hide this. Huh. So this is the disease structure. You have a different sources like PV panels, wind turbines, and storage like UPS and then distributed load. This in itself is a self-sustained system. It can operate without the grid, but generally it is provision is made to connect to the grid, but it can operate without it. So this is the example. One is there are, if you are using wind turbines, as you all know possibly, that there are mainly two configurations of wind turbine based DGs. One is the full power converter, which uses either induction machine or permanent magnet synchronous generator, and other is the partial power conversion topology, which uses the doubly fed induction generator. Similarly, you have structures for PV, and at different ratings they connect at different. For example, if you do only 440 volts, is usually single phase. You can have three phase connections also. And this is what I was saying. Normally, DGs will also operate with the connection with the grid, but if there is a fault in the grid, the DG may isolate itself so that the grid fault does not affect it and continue serving the local loads. So how do you control this? This is one idea of control. This is called hierarchical control. There are three levels. You have the DGs with their local controllers, and then you have primary control, secondary control, and tertiary control. What are the functions of this control? In the primary control, you have voltage or VAR control, frequency control, protection, grid connect, disconnect. These are mostly the primary control and generally done faster. In the secondary control, you have optimization, that is, you have to optimize the resources of the DG. Black start. What does black start mean? Suppose there is a fault in the grid, you have disconnected from the grid, and also the whole DG system also for some fault has shut down. Then you will have to start from zero. That is, there is no generation. Your DG system should be capable of starting from without any external energy source. Forecast. Since many of the DGs are dependent on renewable sources, forecast plays a very important role. In fact, forecast and optimization, these are very interrelated. And on the tertiary control, it is mostly SCADA and market participation. Now, when you have not a single microgrid possibly, but a cluster of microgrids with sufficient energy and power handling capacity, this can be considered as a power plant itself. It's called the virtual power plant. And this kind of virtual power plants can also take part in electricity market. We will concentrate mostly on the primary part. So what does the primary control do? It basically sets the voltage and frequency of the AC bus of the microgrid. So this current control loop, voltage control loop, virtual impedance control loop, these are actually the job of the local controllers, which is done with the local control. So generally, this is done using droop control. So usually there will be some variation in the voltage level and the frequency level, which needs to be restored by the secondary control. So these are some of the structures of the current inner local controller, which is the current control. And I'm sure you are familiar with this. This is the top one is what is called the synchronous reference frame current control. It is usually controlled in the grid voltage oriented reference frame grid, or you can say the microgrid also. oriented reference frame, and the bottom one is showing the stationary reference frame control, which uses a proportional and resonant controller. So how do you do the frequency and voltage regulation? This is the loop that is being shown. So this is group based power sharing control. This most of these DGs will have one of these PWM inverters and a filter at its output, and they are, as I said, they are mostly group controlled. So this is the job of the primary controller, and this part is the local control. So this is the same thing which is being shown in a block diagram form. Now, interesting thing is that this droop is done using a virtual impedance. That is, you can program a impedance so that the voltage and frequency will drop accordingly. The next job is grid synchronization. As I said, that a DG may operate synchronously with the grid, main grid, or it can disconnect. It is done using a bypass switch. So there are reasons why you want to disconnect. This is called islanding, and there are many islanding techniques also. But once it disconnects, it has to generate its own voltage. But suppose after some time you want to connect back to the grid, so a synchronization procedure is needed. There are many methods that has been discussed in the literature for synchronization. This is one of them. Basically, what you will have to do is that you will have to sense both the grid voltage and your grid side voltage and the microgrid side voltage, and make sure that the voltage magnitudes, frequency, and phases match before you close the synchronization switch. There are many ways of doing it. This block diagram shows one. This is a continuation of the same thing. This shows how these differences are mitigated. So just coming to some specific examples, suppose you have a PV array. What are the controls that needs to be done? So at the very basic level, you have the current voltage control and grid synchronization. On top of that, you have MPPT control, then anti-islanding protection that I have not discussed, and active power limiting. This is kind of, you can say, primary control. Then on the next level, you have grid support, that is LVRT or other kinds of support, PV panel monitoring, weather forecasting, fault ride through, energy storage, and these are the secondary control. Of course, protection is not a secondary control. So this is the similar thing for a wind energy based DG. So there are one of the major criteria in the secondary control is the grid voltage ride through. Many countries have different specification for this low voltage ride through criteria. It basically means if there is a temporary fault on the grid, then a DG should not disconnect for the grid provided it is in the light gray, that is zone B, or zone, it is in the zone B. But it can disconnect if it is in the zone C. That means it is a combination of a percentage of voltage dip and the duration for which the dip persists. Depending on that, this LVRT specification has been made for different countries. Not only that, this is the LVRT region. It shows that the normal operating range, what should be the active power injected and what should be the reactive power injected. These are the some of the frequency and voltage tolerance limits that the DG should maintain. Now coming to active power control, most of the time, as I said, that the energy available from the renewable sources is variable. Generally, most of these DGs, call it wind or PV, they usually follow the maximum power point. But there may be situation where your system cannot absorb the amount of power that is available. In that time, you need to reduce your generation. But please note that whenever you reduce, there are some slopes that you should maintain. That is, you cannot suddenly reduce the generation. It has to be done with certain slope, which is also mentioned. And if you also want to ramp up, that also has to be following certain slope. These control features have to be included in the primary control. So now I'm coming to the another major issue. That is the protection of the DGs. Now fault current contribution. Now problem is most of the DGs are interfaced using a voltage source inverter or some kind of power electronic converter. আমার একটা মিটিং আছে। So these are some of the problems when you come to protection of a distribution network when DGs are present. Let us see. The first case shows a situation where you have the utility grid coming through this and there is a DG unit here and there is a fault before this CB8. The problem is that CB7 sees the fault current contribution only from the grid. It does not see the fault current contribution from the DG. So even if it is a severe fault, this CB7 may not trip. So this is called protection blinding effect. The opposite thing can also happen. Suppose the fault is on this side. Now not only the utility grid, but this DG will also hit the fault. So as a result, one of these circuit breakers can trip. Now suppose the third situation is where there is a fault and CB1 has disconnected. But now the fault is being fed by the DG and DG current do not exceed certain maximum limit. So the point is the CB3 may take longer to trip. So when you come to protection schemes for distribution network where distributed generators are present, you will have to think differently. In fact, the distribution protection system what was used for the traditional power system will not work. In fact, you have to bring in some amount of protection philosophy that are used for the transmission line. Other than that, there are other ways to do it. Now, when a DG limits its output current, it does so by reducing the output voltage. In fact, output voltage can get distorted also. So instead of just current-based protection, people are also thinking about measuring the voltage and see the amount of reduction, and based on which you can take a decision on the fault. Other thing is that adaptive DG protection, the over-canal relay, instead of fixing a constant pickup current, you can adapt that pickup current depending on how much power the DG is sending. You can combine different types of protection because a single protection may not give you the optimum result. And you can also do it based on communication. That is, if there is a fault in one point, its effect will be felt in different way in different parts of the distribution network. You collect the data from all the network and then centrally compute it and arrive at a decision, and that you deal with that you do the protection. Now, so far what I have talked about is what is called the centralized control. It has primary control, secondary control, and tertiary control. In each cases, you have a central controller. Now, that concept is slowly being replaced by another concept called the distributed control framework. The reason being, the centralized controller has several problems. Let us look at this. Distributed controllers require less computing power. If your distributed generation system or microgrid is large, your computational requirement will also be large. And the problem is, upgrading it will be a problem. Because if you keep on adding newer generators and newer microgrids, then sooner or later you are going to run out of your computational resource. Secondly, the distributed control systems are robust to single point failure. That is, as I said, there is a central controller in the hierarchical control system. If that controller fails, whole of your DG goes out. So how does it work? Basically, as I said, each of these local units in a microgrid has a controller. You have a intelligence there. Basically, the job of this primary control or sometimes even secondary control is done in a distributed manner by this local controller, so that you do not need to communicate with a central controller, but communication is of course needed between the different units, which are usually closely spaced, so communication delay is reduced. So primary control, many of the tasks can be done whichever we have called by about like virtual impedance control, virtual adaptive group control, synchronized reactive power compensation. All these things, it has been tried on distributed net control system. Not only primary control. Now, as I said, one of the major function of secondary control is the optimization and forecast. So this is how the whole thing goes. You first forecast, create the day ahead schedule, then you do a short-term forecast. That is, once you on the day, every 15 minutes or so, you do the forecasting, and then you do the redispatch and the real-time operation. So this is the framework this microgrid optimizer does this. Okay, but this is what is done in a hierarchical control. In a distributed control, secondary control, the same job is done by individual units, and they try to optimize their own operation. Yes. And it turns out that in the process, the whole system is optimized. So this is what we were talking about in the beginning. This is the virtual power plant. Now we are coming to a situation where there are several microgrids which are independent of each other, but they connect to a same point. They are interconnected, and then they also connect to the main grid. Point is that now these things, these microgrids, they are distributed over a large geographical area. Yeah. Hello. Hello. They're distributed over a large geographical area and have considerable amount of generation and power capacity. So these things, this cluster of microgrids themselves can be considered of as a power plant, although you cannot localize where it is. So it is called a virtual power plant. But it can do all the functions of a power plant. So network microgrids and multi-cluster microgrids, geographically distributed, and the thing is that there is very little communication between individual microgrids or clusters of microgrid. So VPP interfaces with the transmission system. There is no longer distribution system. The feeder head. The VPP can provide transmission system primary frequency support, reactive power support, and energy market participation. So the question now is how to optimally do these things. Again, this is done in a distributed fashion. There are two algorithms that have been proposed in the literature. One is consensus-based algorithm, another is gossip-based algorithm. So there are certain policy aspects if you want to promote the distributed generation. So feed-in tariff, the most common and effective policy measure, has three main factors: guaranteed grid access, long-term electricity purchase contract, trading energy at market value for individuals. Now this is still not the case here. If you have a rooftop, then you will have to sell possibly at 2 rupees per unit. It is not market price. Eco tax, provided tax breaks and grants for setting up renewable energy based DG units, increased tax or fine imposed on utilities that causes pollution, and renewable energy certificates. These are some of the policy aspects that are relevant in the Indian context. Newer policy measures are also being thought. So these are the steps that are being thought. So coming to the conclusion, the effect of DG on distribution network depends on the power flow in the network. If the generated power is smaller than the consumed power, the changes in the voltage profile are acceptable. That is if your DG is small size. But large generation can cause voltage profile, and frequency problems. Now, short circuit power in the grid rises because of the DG short circuit current contribution. Additional fuses on the LV may have to be added to ensure security. Reverse power delays in the mesh system may have to be replaced, as they may trip when DGs on the LV are delivering power to the MV level. You cannot now say that the power is flowing only in one direction. Losses in the distribution networks are reduced. As I said, if you are generating close to the consumer, then losses can reduce. Network reliability can be affected. Network reliability can be compromised if the grid supply is very... Hello?
Yes. Any questions from participant
Yeah.
side?
Yes.
Sir, just I want to know more.
You are not properly audible.
Okay, sir. Just
Yeah, please.
regarding that virtual impedance control,
Uh,
can you please explain a bit more?
Let me go back to that slide. This is the one you are
Yes, sir.
talking? Yeah. So what is it? The voltage control loop, current control loop, and then the inverter. So you are
Okay,
sensing
sir.
the current, and then what you are doing, you are assuming that is as if at the output of the inverter, there is a impedance Z0S connected. Okay.
Okay, sir.
So you set the, see, from the PQ calculation with the group control, you are getting certain voltage reference. But then from there, you are subtracting that I0 into Z0S, so that it is acting like a source with an impedance of Z0S, although actually there is no impedance. Okay. But
Okay,
the
sir.
voltage is dropped like that. See, the actual
Sure.
group control is happening in the on the bottom side. Okay.
So input, it is coming from the current feedback and it is compared with the reference voltage, output
Yes.
of
So
the virtual
see,
impedance.
now let us start from the bottom. First, you are measuring P and Q. Okay.
Okay, sir.
And you have certain references from the secondary control of the P and Q. You comparing them, and you are following a group characteristics there itself. So that itself is telling what should be the magnitude of V0 and what should be the frequency. Okay.
Okay,
So
sir.
you generate the reference wave E sin omega t, where both E and omega are variable. On
Okay,
top
sir.
of that, you are providing a virtual impedance. Okay.
Okay.
Hmm.
No, regard how that virtual impedance is implemented and
No, it is just
it is
calculation.
impedance of
It is
what?
just
The
calculation.
system,
It is
inverter.
just calculation software. There is no harm. There is actually no impedance. So you take I0, I, and then say if there was a impedance Z0 at the output of your inverter, how much drop would have been there?
Uh-huh.
Okay, you calculate that drop and subtract from your reference voltage.
Okay, sir. Okay. Okay, sir. Just to compensate for that droop.
Yeah, yeah.
Compensation, droop compensation. Okay, okay, sir. Okay, sir. I got. Thanks, sir.
Hmm.
Any
Any other
more
question?
questions from participants? So I think there are no more questions from
Thank you
participant
then.
side.
Oh, no, sir.
I believe we
Thank
are
you,
a
sir.
little over the time.
Thank you very much, sir.
Thank you. Let me
You have
stop
given.
sharing.
So thank you so much, sir, for such informative session on like different aspects of virtual power plants, different control, like primary, secondary, and tertiary. And we are very glad to having you as a part of this conference. In near future, we look forward for your contribution towards our towards like such workshops or conferences. Thank you so much,
Okay.
sir.
Thank you. Thank you. Thank you. Okay. Okay. I will be leaving the meeting.
Acha. Hello. In this link, we will continue now with the online.
Yes, sir. Yes, sir.
Okay.